Hello everyone, my name is Meghana Gorli, and today, along with my team member Akshara, we are presenting our work on analyzing missing values in antidepressant drug use as a part of our HAP 786 project under the mentorship of Professor Farooq Alemi. This project is focused on an important challenge in the realm of mental health, predicting individual responses to antidepressant treatments using large scale medical data. Our aim is to support the development of personalized treatment recommendations that can improve the quality of care for patients with depression. To begin with, let's understand the context of our study. Depression is a serious and prevalent mood disorder that affects more than 280 million people globally, as per the World Health Organization's 2023 report. It goes far beyond just feeling sad. It affects a person's energy levels, motivation, appetite, sleep patterns, and overall ability to function on a daily basis. While antidepressants are the primary line of treatment, the effectiveness varies dramatically from one individual to another. These medications work by correcting chemical imbalances in the brain and include several classes, such as selective serotonin reuptake inhibitors like fluoxetine and sertraline, serotonin norepinephrine reuptake inhibitors like venlafaxine, tricyclics, and monoamine oxidase inhibitors. To introduce this, antidepressants aren't one size that fits all. Despite being the most common treatment for depression, antidepressants vary widely in effectiveness from person to person. The trial and error process is costly. Many patients endure a frustrating cycle of switching medications, often over several weeks or months, while still experiencing symptoms and side effects. Our project addresses this clinical gap. We aim to predict individual responses to antidepressants using real world data by decreasing uncertainty in treatment selection. This is about more than just data. Our work is about people, minimizing suffering, improving care, and accelerating recovery for those with depression towards a future of precision psychiatry. Our approach can enable personalized data driven medication decisions to help predict who will respond to which antidepressants. Our main objectives for this study are to address and utilize missing clinical data meaningfully. In real world data sets like all of us, missing data is inevitable, but it can still be powerful if handled properly. Utilize the All of Us research program. It is a large, diverse, nationally represented database which represents people across various demographics and health conditions. Ultimately, our goal is to enable personalized treatment recommendations in mental health care, improving outcomes and decreasing the burden of ineffective treatment trials. Now, let's talk about the structure of the data. The unit of analysis in the study is the individual participant. The dependent variables or targets are the response to antidepressant medications. They are demographics, condition, measurement, observation, procedures, and antidepressant history. The independent variables we included are a broad range of predictors, such as all diseases, all medications, and certain procedures. We further work to build a comprehensive view of each participant's health journey to support modeling. Creation of database. Creating a usable dataset was a crucial step in this process. We approached it in three phases. Cohort construction. We selected all participants from all of us dataset. Initial database creation. This involved compiling a demographic dataset, including variables like person ID, sex, date of birth, and sex at birth, adding target concepts. We used Jupyter notebooks for this process and worked with structured data files extracted from the All of Us research data depository.
We then generate each participant's antidepressant history. The objective is to construct a timeline of antidepressant usage per individual. We first created a concept set for patients with exposure with antidepressants, other antidepressants, and antidepressants in combination with psycholeptics. Using that, we created an antidepressant dataset for drug exposure in all of us, utilized background notebook-based workflow with support for the long-running code for approximately 15 to 24 hours. We calculated end date, dosage days, depression episodes, and remission events prior to current trial. checked if the dosage days for any trial is greater than 7 days, and created a new column dose 70p for it, calculated for age at depressant trial start, and categorized them into predefined age groups. We also created features for antidepressant history response by initializing four new columns, which is SN, history of taking same antidepressant, no remission, SR, history of taking same antidepressant with remission, DN, history of taking same different antidepressant, no remission, and DR, history of taking different antidepressant with remission. Through this, we analyzed antidepressant history and response by categorizing antidepressant use and tracking remission patterns. This produced a well-structured data set, and we named it as AD underscore history underscore DF. Once we generated the antidepressant history, we needed to merge the dataset with other clinical information. This also involved dropping duplicates, filtering changing data types, and aligning with the standard coding systems like SNOMED, RxNorm, and ensuring a clean and unified dataset. For dependent variables, we initiated targets underscore DF, and for independent variables, we initiated medical underscore events underscore DF. The final target TF obtained is 527 and medical events TF obtained is 41,480. Testing target and medical event tables ensures that the data is properly structured and accessible for further analysis. After merging the data, we proceeded to analyze predictive features using likelihood ratios. We calculated likelihood ratios for medical events. This is a key statistic for evaluating the relationship between medical events and the target group, calculated the total number of unique individuals in each group in the overall occurrence. We calculated and stored the likelihood ratio for each medical code. We downloaded 351 likelihood ratios. This helps to quantify how strongly each medical event is associated with the target condition. Likelihood ratio greater than 1 implies a strong association with a positive response, whereas likelihood ratio less than 1 indicates a feature associated with a poor response. This helped us to rank predictors. This is a We finally had a robust data set aligned with clinical standards and ready for advanced modeling techniques. Here's a representation of the data set that shows from one of the files that we downloaded from the likelihood ratio files. So, coming to the conclusion, this dataset is now suitable for lasso regression, machine learning, interpretability pipeline, and predictive modeling. So, we successfully implemented a structured approach to clean, merge, and analyze large scale clinical data. And our goal is to use these models to predict antidepressant response and potentially integrate them into clinical decision support systems. This framework can be extended to other drug classes too. And looking ahead, we see vast potential to extend this methodology across different pharmacological domains. Our ultimate aim is to enhance clinical decision making with predictive insights, making treatments more personalized and effective. Thank you for walking through this.